question about stretching, compression, and so forth as applied to linear functions. So, linear function isn't the best to use to illustrate these things, but even though it's the simplest of the functions, it doesn't have any distinguishing characteristics, just a boring straight line graph, so it's a little harder in some cases to see. So I'm going to give you more of an explanation than is really necessary, but I think it's a good idea to, again, go over the process of constructing a graph by transformations. So we start with the basic y equals x function. We could do a table. We could just slop down a graph. We've got points 1, 2, 3, 4, 6, and the origin is 7 points that have been marked. And I went ahead and marked the negative 1/2, 1/2, and 1/2, 1/2 points that aren't on the table. But this light white line is your graph of y equals x, your basic function. Now, if we do a transformation, most general transformations, a f of x minus h plus k, which is then a times x minus h plus k. Another transformation would be a times f of x minus h, which is a times the quantity x minus h. Another would be a f of x plus k, which is ax plus k. This is the transformation that's the simplest to use, and it doesn't give us, none of the others give us any information that this one doesn't. So this is the transformation I'll use. Consists simply of a vertical stretch by factor a and a vertical shift of k units. So we apply that, and we go ahead and we do the graph of y equals a f of x plus k for a equals 2, k equals negative 2. So y equals then a f of x plus k. A is 2, k is negative 2. You get 2f of x minus 2. And f of x is just x, so it's 2x minus 2. It's a vertical stretch by factor 2. Y equals, so the vertical, okay, we start with the vertical stretch by factor 2. That's the first thing we do because, of course, 2 is multiplied by x by order of operations. We want to do that before we do the subtraction of 2. Vertical stretch by factor of 2 gives us just y equals af of x, which is 2f of x, which is 2x. To get that, we take vertical arrows up to the points of the original y equals x graph, these purple arrows that may be a little bit obscured, but they should be pretty clear here. And we double those because those vertical arrows represent the y values. When we double the y values, we need to use an arrow twice as long. Those are the green arrows that then go up and down to the graph of y equals 2x. And we get the points at the ends of the green arrows, which double the purple arrows. And there's our graph, and it has twice the slope of the original graph. Slope of the original graph is 1. Slope of the new graph is 2. And of course, we know that the slope of the y equals 2x graph is 2. So our vertical stretch gives us the slope of our vertically stretched, a vertical stretch by factor 2 automatically gives us a graph of slope 2. That's not going to change when we do the vertical shift, because the vertical shift moves every point by the same vertical distance. That's not going to affect the slope. So the vertical shift of negative 2 corresponds to k equals negative 2. It's a f of x plus k, which in the case of this example is 2x minus 2. And we accomplish that graphically just by drawing arrows of length 2. Now these arrows seem to have gotten longer as I went up, so that the graph we get from those vertical shifts isn't quite parallel to the 2x graph, but if I'd have used equal lengths, it would have been parallel. Okay, so there's our graph of y equals 2x minus 2. Now I'll point out that any straight line has an equation that can be written in the form y equals ax plus k. Okay, no matter what it is, no matter what form it is, it can be rearranged. If you solve it for y, it comes out ax plus k. And in usual symbols, that's your slope-intercept form, y equals mx plus b. So we observe that m is your slope, that A has the same function m does. It's what you multiply by x, so that a will be the slope. So your vertical stretch is the slope, always. And k is your y-intercept. Over here, k was -2. Your y-intercept is -2 because we used that vertical arrow of length 2, a downward vertical arrow of length 2, to represent that vertical shift. And the origin went down to the point 0, -2. There's your y-intercept. So that this will always be your y-intercept. This will always be your slope. Now we can do vertical compression. Although I don't like that word, I prefer just saying vertical stretch by factor 1/2, which does compress the graph. We multiply by 1/2. And I regard that as still being a vertical stretch, but it's not really a stretch, it's really a compression. Rather than calling it a vertical compression by 1/2, which almost means you do a 1/2, then you do a 1/2 again or something like that. I don't like the language, but that's the language your book uses. And it won't even say by factor. Your book will say vertical compression by 1/2. Okay, well, I'll live with it. I don't particularly like it, but maybe it's just my perception of the language. Okay, so anyhow, we do the vertical compression by factor. We multiply the f of x function by 1/2. Okay, that takes every purple arrow and cuts it down to half its length, indicated by the green arrows. So the purple graph is your 1/2 f of x. In this case, f of x is your basic linear function, f of x equals x, and you get 1/2 x. So there we've constructed the graph of 1/2 x. Wanted a graph of slope 1/2, which this has, through a different y-intercept or through some other point. We can raise it or lower it with a vertical shift to go wherever we want. So we can get any graph we want with a slope of 1/2 by vertically shifting this purple graph. Okay, so that's kind of it.